My name is José Rubio, and well, today I wanted to give a brief overview of what we do at Ommatidia LIDAR. So, well, as the name suggests, we are developing LIDAR systems. I'm guessing that probably many of you are aware of what LIDAR is, but just in case, it's basically a ranging technique based on lasers. It's in many ways similar to radar, but it uses light instead of RF waves to measure the distance to objects. So basically, it provides 3D reconstruction of the scene around the system. So for any given pixel, any given direction, you have the distance to the object. So LIDAR has been probably around for a long time now. I think the first applications I recall when I first heard of LIDAR were related to terrain measuring. So these were LIDAR systems, airborne LIDAR systems on planes that were flying over the surface of the terrain and measuring the distance to build digital terrain models. Since then, it has evolved a lot, and now there are a very large number of applications where LIDAR has a lot of potential. Probably the most important one in terms of the volume of the potential market is automotive, and in particular the autonomous driving market. But still, to make this potential market real, there are many challenges for current LIDAR systems. Some of these challenges are related to the performance of the systems, so the sensitivity they have, or their ability to work, even if there are other similar systems nearby without any crosstalk between them. Also, the ability to work under any weather conditions, or under rain, under fog, without significant performance degradation. So these are some of the challenges. But also there are others in non-functional parameters, like the size of the system, the weight, or the cost of building such systems, which many times are using very complex optics, and this is one of the main drivers behind the high cost, size, and weight of many of existing LiDAR systems. So we wanted to use integrated photonics to change this and to approach LiDAR in a different way. But we also went for nature, looking for inspiration in terms of what architecture to choose in our LiDAR systems. And in particular, we went to look into how nature has solved for insects the problem of capturing light and generating meaningful images in a quite reduced volume. No? This is what these little animals have. So you're probably familiar with how the eyes of insects look. They have this multi-lenslet appearance. Each of these lenslets or elements is called actually an ommatidium, and that's where we derive our name Ommatidia from. And they have inside a number 6 to 8 sensing elements. So when you look at the literature, you see that so simple insects like flies have in total around 4,000 sensing elements. So then you see that more advanced, at least in terms of social interactions, they have insects like bees, which probably need more advanced imaging, because of this more complex social structure, have a higher number of elements. They have up to 40,000 elements. And then on the extreme, you have insects like dragonflies, which are predators, and then therefore they have a need for very accurate and very fast imaging. They go up to over 300,000 elements. We have started a bit far from that. Our first generation devices have around 500 sensing elements, but we are catching up as fast as we can. And actually, our second generation devices will have between 4,000 and 48,000 elements, depending on whether we are talking of the 2D or 3D imaging devices. And with this number of elements, we already expect to be able to deliver a quite high resolution and range performance beyond what's actually possible with the current systems. So how did this inspiration get turned into actual devices. So this is a picture of one of our first generation devices. This is a passive photonic integrated circuit. It's purely akinetic, has no moving parts. But what it does have is a number, more than over 100 of different light collecting apertures. And this, together with the architecture, the way in which we combine this, the light collected with some optical processing and later with some digital processing, allows us to reconstruct the scene in front of the sensor. So in particular, this one is a two-dimensional device, which means that we are able to resolve one angular dimension plus one depth dimension. These first generation devices were allowed us to demonstrate TRL 3.4 at the end of last year, 2019, and with new revised devices, we are aiming at reaching TRL 6 by the end of this year, 2020. So this was mainly focused on the reception side, how to collect light, but there is also the question of how to illuminate the scene. And actually, when you look at this problem for LIDAR system, there's something which is a bit odd. Now we are, the target of the market is to reach 3D systems ranging and measuring at ranges of several hundred meters up to 300 meters, and in most cases with collimated beams, which because of eye safety regulations are limited to a few milliwatts. Maybe a bit more than that if you're working in the 1500 nanometer range, but not significantly more. So this is odd when you compare it with what happens when we ourselves are driving at night in our car. In this case, the lights in our car are providing a few watts, at least 4 watts of optical power into the scene in front of us. We have a quite large aperture in our pupil, especially at night when in low light conditions. It can be up to 9 millimeters, 4 millimeters. And we have a very, very sensitive detector, which is our retina. We know that it's able to detect down to single photon in low light conditions, like when you are looking at the sky at night and you are seeing a barely visible blinking star, that there you are actually detecting single photons. So this is the comparison is a bit odd. How is that we need all this to be able to drive at night, and then we want to do it with such small amount of power, which is more comparable with a laser pointer. It turns out that the only way this is possible is by having some significant trade-offs. The most common one is to do very, very sparse sampling of the scene. So instead of having a dense image, you sample at selected points, and there you turn a bit you have the trade-off, and you are able to collect enough photons for each point. In our case, our architecture is able to work with fluid illumination, so we don't need a collimated beam. We are able to illuminate the full scene at the same time, and this fact enables us to use a lot of power. A lot more power, like more than 1 watt, several watts, but at the same time still being eye safe and comply with all regulations. And still, with our sensor architecture, we are able to reconstruct the direction and the distance from the light coming from any object in the scene. So, just as a recap of what I tried to explain about the main differences in our approach. We are using a purely solid state approach with no moving parts at all, and this makes our solution very compact, very scalable, and goes to high productions. And also the combination of fluid illumination and the fact that we have a high number from hundreds to several tens of thousands of optical sensing elements. And we use coherent detection, which makes our systems single photon sensitive. All these elements together make us extremely efficient in collecting collecting photons from the scene. And this is actually the key difference which enables us to improve the performance of the system in terms of resolution or range or accuracy or a combination of all of them. So in terms of our intended markets, well, of course, automotive is a very large market, which is still a few years from fully developing, but it's very interesting for us. But we are also seeing other quite interesting markets like space, where we have seen that it's very sensitive to some of our advantages, like the reduced size and weight of our systems. And we are actually starting very soon, in less than a couple of weeks, a project with ESA for space meteorology, and also railway mobility, where we have seen that it's actually an application which is very well suited for our first devices, which, as I mentioned before, are measuring 2D, so one angular direction plus depth. Because in railway applications, you have inherently in the application the linear movement, which gives you the extra dimension that you need. We have two locations currently, one in Madrid, in the Space Agency Business Incubation Center, which is in the Science Park of Universidad Autónoma de Madrid, and another one in the Business Innovation Center in Noordwijk in the Netherlands. We started operations as Ommatidia at the end of last year, 2019. We are 4 people right now. Here we have a picture of 3 founders, which together we accumulate quite some experience in fields like photonics, microfabrications, MEMS, signal processing, system integration, and so on. And we have a family of 4, actually now there are 4 patent applications which are in process of evaluation. And that's all. Thank you very much. I'm open for questions.
Thank you, Jose.